So we're ready now to proceed on to the second homework assignment and sort of some basic concepts. And the two concepts we'll be looking at now is comparison of simulation and experiment and how we would address these in communication systems. So let's have a look at the homework assignment. So there's three parts to it, and I'll be going over each of them separately. And I want to tell you what the objectives are. So this assignment is considered to be a learning tool, as all assignments should be. And in the first part, our objectives are to be able to generate theoretical bit error rate curves. So I've presented them to you in class, various equations for how we could generate bit error rate versus signal to noise ratio. And there is in MATLAB a particular tool which is very easy to use and helps you visualize all kinds of different comparisons you might want to make between different modulation formats. So the objective is to be able to work with that tool, which is called the BER tool. And in particular, to use this tool to be able to go by eye and find loss with respect to QPSK. So that will be what I'll be asking for you in that part. So very simple part one. Mostly to get you familiar with this tool, which is available. In part two, we'll be going back to the VSA software, and this time we'll be looking at how the VSA software can help us analyze the performance of higher order modulation formats. So in the last homework assignment, we looked at binary modulation, and we were very concerned with the eye diagram. And now, as we go into higher order modulations, we will be looking at two-dimensional constellations. You can look at the VSA software, you can have a look at the eye diagrams, but we'll be concentrating mostly on the constellations. So understand how to analyze QAM data, and in particular I'll be introducing this concept of EVM, which stands for error vector magnitude, and I'll be talking to you before the assignment in a capsule about part two, where we learn what this figure of merit is for the performance of a communication system. So in addition to knowing what EVM is, we'd like you to understand the advantages and disadvantages of it as a quality measure or as a figure of merit. In particular, it's important to know the relationship between EVM and signal to noise ratio, and in particular how we can contrast bit error rate and EVM, and under what circumstances they would be equivalent, and where they would be different. So after we finish with the VSA software in part two, we'll move on to part three, where we will be doing a simulation. So if part two was supposed to be a facsimile of an experiment, a virtual experiment, part three is where we get into simulation. So we would like to use Monte Carlo techniques in order to estimate bit error rate. So this will be my introduction to you of this concept, and then later in the course, when we get down to the second series of homework assignments, they will be based entirely on doing a series of Monte Carlo simulations. So this is your introduction to that concept. So I want you to understand what a Monte Carlo system is, why do they exist, why do we use them, and in particular to use BERT in MATLAB to run your Monte Carlo simulations. And in the future, you may or may not use it, but I think it's a good way to understand what some of the concepts are in exploiting Monte Carlo by using the bit error rate tool. So we'll start with part one of the assignment. And in part one, you're basically going to complete a table. And in this table, we have several modulation formats in the first column. And you will be taking each one of them, and you're going to give me the loss with respect to QPSK. So firstly, I want you to just write the equation for me. So the equation comes right out of the notes, what I've presented to you before, but it's just like to center your head. Write it down here so we know what we're talking about. Then you'll actually plug in the numbers. So first is an equation. Now you come back with a numerical one because you'll say m equal 8 for 8FSK, m equals 16 for 16 QAM, and you'll replace m in the formula with the right value, etc. And then finally we're going to move to BERT tools, where you're going to go and plot the bit error rate curves and then look at asymptotically what the loss is. So one is a graphical. So this would be a graphical report of the value. And this one would be a calculation. And this would be the equation. So remember what the loss compared to QPSK, what the definition is. It's related to the so let me remind you about what the loss compared to QPSK is. Remember, it's related to the small d min, which is we set equal to the square root of the loss times the square root of 2. So if you want to report this in dB, you would say it was negative 10 log 10 of the loss. And so we have various equations for small d min for different modulation formats. You would plug in that equation, and then you would solve for the loss and report it in the table. So just to remind you, we have already looked at 16 QAM, for instance. And in 16 QAM, if you look at our notes, we would be able to take the equation here for dmin and put it into the equation so that we can look at what the loss with respect to QPSK is. And here is the theoretical value. And of course, we'd have to replace L with 4. And if we did that, we would come up with a 4 dB, which we had found previously. Then the next step would be to go into BERT tools. I think the example I have here is for 64 QAM. But of course, you'll be doing it for each one of those modulation formats. So you open up the BERT tool in MATLAB, and you will be presented with this pop-up window. And you can see there are 3 tabs here, and we'll be interested in the theoretical tab for part 1. And this is going to generate a bit error rate curve. And so you can specify here the range of EB over N0. So EB over N0 is like a digital signal to noise ratio, and that is the range that will be plotted. Channel type will always be using additive white Gaussian noise for this homework assignment. And here you can see you can put in PSK or QAM. Use the drop-down menu, just pick the modulation format you want. And of course here you're choosing M. Don't worry about the differential encoding. We'll not be using that. No channel coding, etc. So once you've finished choosing what you want plotted, then you hit the plot button. And when you do that, you'll get something that looks like this. This is the case for 64 QAM and QPSK. And your assignment would be to look here and figure out graphically what the loss is of one compared to the other. And so you would just see how wide that is and the scale that's been plotted. So once again, this is the table that you'll be completing for part 1. So let's move on to part 2 of the assignment. So for part 2 of the assignment, the most important thing you'll have to learn is something new. Is called the error vector magnitude, or EVM. Very important figure of merit that's used in communication systems, and I'll be telling you why it's interesting and how in particular to exploit it. So let's start first by looking at another concept, which is how you would experimentally measure the bit error rate. And to do that, you would use something called a bit error rate tester. And the bit error rate tester sort of looks both at the transmitter and the receiver. So you have a transmitter side and you have a receiver side, and you're sort of cheating in your bit error rate tester because you're looking at both the transmit and the receiver. And then of course you have some system under test, and you're trying to figure out what is the bit error rate of this system. That's your goal. And so what you do in order to determine what the bit error rate is, you start with a common clock source because we're synchronizing our transmitter and our receiver. And what you do is you generate a whole bunch of bits. You send them to the system under test, and then because you have this back channel, that means you know what pattern of bits you send, and because you know the bits sent, well, you can determine whether an error was made or not. So in particular, the pattern generator uses something called a pseudo-random binary sequence, and we'll probably hear a little bit more about that later in the course. But for now, pseudo-random, it's not really random, but it looks pretty random. And that's what is generated, a controlled sequence. The data is known at the receiver because I have this back channel. They're really in one lab. This one bit error rate tester handles both the transmit and the receive. And because of this, we're able to measure the bit error rate. So I can see what bits were sent, what was received, and if errors occur, count errors, I get the bit error rate. When you were looking at the eye diagrams previously, let's just think about what goes on in the binary case. In that case, we had this eye opening, and one of the things we did in the last homework was to determine when would be the best sampling time. And then knowing that this is the best sampling time, we sort of took the midpoint of this opening and said this should be our threshold. So what's kind of interesting and what happens in a bit error rate tester is they don't know exactly what the sampling time to be, and they certainly don't know necessarily what the optimal threshold is. So what they do in this device is they actually just try a whole lot of different values. They try a lot of different sampling times, and they try a lot of different thresholds. They do a whole bunch. They measure the bit error rate at each one of them, and then they pick the best one. And so that is their estimate. And so, like here would be some area where they're getting essentially similar performance. And so any of these, it's close enough to the sampling, close enough to the threshold that it doesn't really matter. And this would give you your estimate then of the bit error rate. Yes, timing and threshold. And nice animation there. Okay, so this is the bit error rate tester. That's how it works. That's how it can come up with a good estimate of what the system performance is like. But it is a very expensive piece of equipment. And of course, it requires that your receiver and transmitter be co-located. So this is not always possible for the system that you would like to test. So going on, what would happen if I did not have this connection? I did not know what the data really was that was sent. What could I do in that case? And that is our reason for looking at error vector magnitude, because it is a way of getting quantifying the quality of the signal without necessarily having recourse to knowing exactly which data was sent. So moving on, what do we do with EVM? Well, let's get away from the simple binary case and let's start looking at an M-ary case. Here we have 16 QAM as an example. And here is a received constellation. So I don't know what was sent. I only look at my receiver. I plot my coordinates that I've received, and I get a bunch of received points that you see as these red points. In black here, I have written, these circles around them, and they're like where I can see evident grouping of symbols. And I look at that and I think, well, probably all of these red ones here, they probably belong to the constellation point that's right in the middle of that. Probably a little bit of noise has nudged it away from the exact point because that I get over them. But I don't really know the truth, okay? So I'm guessing. I don't know the truth. So what we're going to do is we're going to assume that the nearest symbol is the true symbol sent. So I don't know the true symbol, but this is going to be my assumption. I'm going to assume that the signal is good enough that the closest one is right. And you're going to tell me, well, if that's true, then I'm never making an error. Well, sometimes you'll make an error, but most of the time, if it's a good communication system, most of the time you're not making errors. And so this is the motivation for this assumption. So here's the idea. I have inside of this cloud that I drew here, there's the the center point, which is what I believe that the receiver is, like what was sent. So I put that as my true. I assume that, there's some true one. I assume the true one is the closest one. And then I have this red cloud, which was around the nominal center of the cloud, the nominal transmitted point. And now I look at each one of my little scattered red dots, and for each red dot, I look and I ask myself, how far away from it is it from what I believe to be the true one? I'm not sure if it's a true one, but if I'm going to, for the sake of assumption, I'm going to assume that was the true one. So now I can quantify how far away from it is. And so it gives me an idea of how much error there is in the system, how much noise there is in the system, how big is that cloud of dots around the presumed correct one. So how close is it? Well, let me quantify how close it is. Now I have n different points scattered all over this constellation. So for each one of those, I'm going to get one value, which will be the length of this, what I call the error vector. So the error vector from the presumed true point to the received point, each one of those n, I have a vector, which is a difference, and I measure how long is that vector. And so I come up with this. And of course, that's for each point. And then what I can do is I do the summation over all of these points. And this summation, and I average over them. And this gives me what I call the error vector magnitude. And it's in a percentage because I will normalize that to the largest symbol distance. So I have some absolute measure of the largest distance in the constellation. So this is the error vector magnitude, and of course I don't need to know what the true one is. I just have this assumption of what the true one is. Of course, it's a little optimistic as a measure, figure of merit, because sometimes, of course, it won't be the true one, and that the error vector is actually be much larger because it would have to go up to another nearest neighbor, which was the true one set. So it's a little optimistic, but we'll see that it's still a very useful metric that we can use for performance. So what happens if I have small EVM? If the AVM is small, that's because the constellation is very compact. Compact in the sense the little dots, the little received signals around the nominal true values is very compact, so there's very little noise. So a scatter plot is kind of similar to an eye diagram. So it is an indicator of signal quality without necessarily being the definitive bit error rate. But very simple. So I can just look at the constellation and get a feel at a glance for how good or bad the signal quality is. So what is the difference in terms of bit error rate and EVM? Well, first of all, for bit error rate, we know the true bits. That's a big difference. In EVM, we assume that the symbols are not wrong, but they could be. So it's quantitative because I measure it. I mean, there are lengths and I calculate it, so it's quantitative, but it's based on a pretty strong assumption. But if the signal is good, if we're in a regime where the probability of error is low, it gets a good quantitative measure of how good is it. If it's good, it works well, and it tells us how good it is. So the relationship in general can be given by this simple equation, that the EVM is roughly equal to 1 over the square root of the signal to noise ratio. Okay, so if this were true, then if I estimate EVM, then I would have signal-to-noise ratio. And then from theory, I could take my signal-to-noise ratio and I could estimate bit error rate. So EVM is also a conduit that sort of lets us come up with an estimate for bit error rate, even if we do not have access to the true symbols, true bits transmitted. So it's not exact, I said, more approximately. And so it's not a perfect one, but it is like I said, a conduit, a method of trying to get bit error rate, even with a test equipment, which is much less expensive, or with a setup where I don't necessarily have the transmit and the receive information together. So this relationship is based on this assumption that you're not making any errors. So this is a plot of signal-to-noise ratio versus EVM, and suppose that this relationship is true. So this plot that I'm showing you is just 1 over the square root of the signal-to-noise ratio, which in this case is in dB. So this is just the simple equation. And then I'm going to now look at what would be the EVM if I really did know the true data bits. Okay, so if I knew which was the true data bits and I was going to calculate it, I would get this nice line with the circles on it. So that's like the true EVM, and you can see that for most of the curve it's dead on. Maybe an extremely bad signal-to-noise ratio where this is like awful, where the noise is bigger than the signal. So clearly it's a very good estimate for almost everywhere, this relationship. But of course, that's if I could really tell what the true ones were. Now what happens if I don't know? This is without knowledge of the true one, because for each bad signal-to-noise ratio, I know on average how many times I'm going to make an error, and then I'm going to do a bad job on the EVM. So I can plot this, and you can see that it varies from BPSK to 64 QAM, and not surprisingly, the more sensitive the modulation format is to noise, the less good this estimate is. But for BPSK, of course, it's very close to the EVM if you had gotten if you really did know what was transmitted. And even if we were to look at the 64 QAM case, which is way down here in these asterisks, if we have a strong enough signal, of course, it starts to be quite close to this ideal relationship between EVM and the square root of the signal-to-noise ratio. Ideal not because it's a perfect relationship, but because it's a true relationship, and that way, once I know EVM, I would be able to know SNR. But of course, never forget that this is overly optimistic. It's going to tell me that the signal-to-noise ratio is stronger than it actually is. But in this regime, very low down, it's pretty accurate. So if I'm working where a strong signal, then most of the time my assumptions about the closest one being the true one are accurate, and therefore the measurements I'm making are probably pretty close to the true value. So for the homework assignment, we're sort of going to be assuming that this relationship is true and seeing what you can do with it and how accurate it is when I estimate bit error rate based on this understanding of signal-to-noise ratio. So this is the help message from the VSA when we talk about signal-to-noise ratio and how it estimates it. So you can see that it's based on the error vectors, so it's basically using the relationship that I just showed you in order within VSA to estimate the SNR. So you'll be looking in the homework assignment to find what it found for the error vector magnitude and what it estimated as the signal to noise ratio.